Hi all, I am K. Surya, working as Assistant Professor in the Department of VCE at SNS College of Technology. So in this video, let us see about inverse Z transform using power series expansion method. So first we will see why we need power series expansion method. So the most compelling reason for using this is that it directly yields the sequence values x of n. By expanding x of z into a power series, the coefficient of each z power minus n term immediately gives the value of x of n. This is a straightforward and intuitive way to obtain the time domain representation. Next one is it's easy to handle complex rational functions. So many Z transforms encountered in practice are rational functions, while partial fraction expansion is also a common technique for inverting rational Z transforms. Power series expansion provides an alternative, especially when partial fraction decomposition is cumbersome or not easily applicable. ROC is crucial in determining the uniqueness of the inverse is a transform. Power series expansion, uh, when performed correctly, implicitly incorporates the ROC information. So the direction of the expansion, positive or negative powers of Z, is dictated by the ROC, ensuring that the resulting sequence is causal, anticausal, or two-sided as appropriate. Next one is in some cases, power series expansion can be computationally simpler than other methods, particularly for lower order rational functions. It avoids the need to find poles and residues, which can be a complex operation. Next is it is used in various applications in electronics and communication field, mainly in say circuit analysis for analyzing and understanding the electronic circuits. Then it's used in signal processing. It is used in filter design in order to design the electronic filters for signal processing, and then in modulation and demodulation, in designing an amplifier circuit for creating and a good amplifier, powerful amplifier. It's used in system modeling, etc. So next we'll see the steps involved in power series expansion. So first we have to represent the x of z as a power series, typically in terms of say z power minus 1 or z. Next, the coefficients of the expanded series directly corresponds to the sequence of values x of n. So for instance, say x of z is equal to summation of x of n z power minus n can be expanded by matching the terms. This is known as term by term expansion. So the region of convergence is crucial here in dictating the appropriate form of the series expansion. So the idea here is to express the SS transform as a rational function. The second step is determine the region of convergence, then choose the expansion variable based on that region of convergence, then perform the power series expansion, then identify the sequence values and then express the result. Let us see few advantages and disadvantages of power series expansion. So it has advantages of say simplicity, applicability to complex is a transforms and directly yields a sequence values. So the method is conceptually simple and easy to understand, and it also can be applied even when partial fraction decomposition is very difficult. The coefficient of the power series directly give the sequence values. Next one is some of the disadvantages here are that obtaining a closed form expression for x of n can be challenging. Often, only the first few terms of the sequence are easily obtained. Next one is the power series expansion is only valid within its radius of convergence, and then long division can be tedious for complex Z transforms. So hope you understood the basics of power series expansion. So let us take up some assessment questions. So first one is, what is the main advantage of power series expansion method over other inverse Z transform techniques? Next one is, once you have expanded the Z domain function into a power series, how do you identify the time domain sequence x of n? Next one is, in which specific scenarios is the power series expansion method preferred over the partial fraction expansion method? Thank you for watching this video.